in there. Okay. It says on there, but there's a lot of background noise. Let's see if I can get rid of the background noise. Oh God, that's all I hear is background noise. Let's turn this one on. Which one was that? All I hear is background noise. All right. See if I get it. All right, there we go. It should be, in my opinion, such that I walk into the classroom and this is already done, but I don't have that choice. So, this is life in the fast lane. And the autofocus, I don't know what's up with the autofocus there. Okay, so let's see. Okay, so we went to the point where we did, if you've seen some of the stuff, I'm going to turn it so that it's like that, then turn this. There we go. So now, let's see. This nasty piece of crap out here. Okay. Let's see. So that is where we want to be. Oh, and I'm all the way in the back. Oh, that's the, wait a minute. Okay. Oh, that's the appendix. Okay, that's kind of where I wanted to be. However, I guess I'm at the end of that. So this is the area that's talking about the parabolic motion. So we did that. That was last time. I did one problem. Did I complete it? I don't know. It's out there on the record. But let me slide into this. I think the next one is something that you've seen before. It's yeah, because I've written all over this thing. And so this is something you've seen before. It's the curvilinear motion. And so he has all this setup up here, which actually is just, his way of determining what the tangential direction and the normal directions are. So he has a tangential direction, so if it was over here, it would be tangent that way. If it was back here, this would be tangent. And so these are the base vectors. So bizarrely, these do change and they flip around. So this is kind of disconcerting if you were trying to track things through time. But usually what this does is it focuses on a certain point there. So that's not bad, but it turns out he goes through the derivation and shows eventually this thing where you've seen, Now, you may have seen it as R in physics, but it's the same thing as rho here. So he has decided to call his distance rho. Did y'all use it as R? I think you used it as R in physics, but I don't know. Who knows? So what happens here is the tangential acceleration becomes the change in speed. So if he was going 80 miles an hour here, and 80 miles an hour here, 80 miles an hour the whole way through, then his v, which actually, he should actually have a subscript t to delineate it from being the difference between the other one, but that's okay. It's okay. So actually, his v is that, and if you go down, you'll find the acceleration, which actually is on the next page, becomes nothing more than the change in the velocity. So if he's going 80 miles an hour the whole way, then v dot's equal to 0. He's not increasing or decreasing his speed. Now what he looks at, or starts to look at, is this. So this base vector does change, and okay, he comes up with a kind of a strange way of doing it, which is okay. So he basically takes a delta theta and relates that to dt, and he does it through this whole thing where he comes down and eventually determines, he determines that that is the case. And it turns out in a minute, or maybe next time, it turns out that's related also to polar, which I'll relate, when we get to that polar section, I'll relate it back to here. And what you find out is, let's see, he doesn't list it yet. Oh, he does. It's right here. So you've got this, which is the change in the speed, and then this, which is the term you've seen before. So if the dude's in a car and he's just going in circles around and around and around, then his R or his rho doesn't change, it remains fixed. So then the question is, what happens if it doesn't? If it doesn't remain fixed? Well, I guess I should have said something about that. Then he gets down here. No, we're not particularly interested in 3-dimension, but there's a thing called an oscillating plane, which obviously that thing can move around. So it's a little bit annoying there. Okay, he's not doing that yet. Wait a minute. I think he embeds it very quietly. Yeah, he embeds it, it's right here, but I don't see, oh no, I'm sorry. He does put it in here. He puts it in his procedure. You get down here, and you realize this. If the path is expressed as something funny like that, that's not that funny. The radius of curvature at any point, then the path is determined from this. And this, I don't know if it's, which calculus it's in, but I think this is derived in that calculus, but I'm not sure which calculus. Oh, okay, standard calculus text, but I don't, they break a standard calculus text into, what, 3 classes? So all you have to do is take this derivative, take it twice, stick the first derivative right here, square it, and you have the 3/2. Take the second derivative, take the absolute value in the bottom. So here, is it this one? Yeah, this one he comes up with case in point. So there's only 2 types of problems in the whole text. Ones in which rho's just fixed or given, okay, and then you don't have to think about that. And then there are problems in which it's written like this. If it's written like that, you've got to take a derivative once and then take a derivative again. So if you notice, what he's done is take the first derivative of this thing, and he doesn't oh yeah, I'm sorry, he does write it down. Wait a minute. Okay, does he? Yeah, he writes it right here. And then you have to take the derivative again, but for some reason, he wrote it all the way down here. Now, once you have this, here's the key. You have the second derivative is not, in this case, not always, but in this case, it's fixed. The first derivative is not fixed. So you have to determine where this skier is. No, that's not exactly. But what's funny is, if you get down here, so this is x equal to 10. If, say, you were at x equal to 5, the radius of curvature would be different. And the reason it would be different is because of this term. So if you notice what he's done, this is what I'm getting at. He's made this generic. So right now, rho is a function of x. But he still has an x stuck in here. Then all he has to do is stick in 10 for right here, and he gets his number. There are cases in which, hang on. There are cases in which why does the screen look so funny up there? Okay, hang on. I'm trying to adjust it in class here. And that little bar, I can't get rid of that thing. That shouldn't even be there. How do you get rid of that thing? I guess you don't. I guess it just stays there. Okay, so all he does is stick in this, sticks in his velocity, and that's it. Now, how did he get the 2? This is the thing. If you look back at okay, it says his speed is 6, and it's increasing by 2 meters per second squared. So that's the acceleration tangential. So what you do is you use this to find the acceleration normal, but you also have to use the rho. And so you grab the v here, and then you grab the rho here. They all look the same. So there are only 2 types of problems. Here's the other type. The other type is it's just fixed. So he's going at a rate, speed. Okay, if the car increases at a speed of a constant rate of 7, so what you have is acceleration, tangential, and I guess he's still using u tangential plus, and just cut right to the chase, u normal. So you just put in that. Then, okay, wait, if the has a radius of, car increases at a speed, starts from rest, determine the time needed for it to reach an acceleration of 8 feet per second. What is the speed at this instant? So if it's starting from rest and it's accelerating at a constant rate, v is equal to v naught plus acceleration t. And his acceleration was 7. His initial, it started at rest, t and equals to v. So what you do is take the 7t, stick it up here, in here, square it. You don't have to worry about the rho, it's just given as 300. And then you end up having to do square root of a squared, which is increasing at a constant rate of 7, plus this squared. So that squared and that squared again. So what you find out, so he has the same thing here. Then he has the normal. And so he ends up with a t squared. I'm not going to calculate the 7 squared divided by the 300. So he has it. And then what you find out You end up with a t to the fourth, and you're forcing it to be 8. You monkey around with this, you square the 8, you move that over, you move the 7 over, you end up with so many seconds, and then you can put in the speed at that point. So he's backed you into a corner here with a funny way of asking a question. So there are weird things like that. So there are 2 types of problems, but some weird kind of questions that could be asked. Oh, here's a good weird one. That's sickening. That's almost so weird. So, here okay, so the boxes are traveling along this thing here. And it shows it starts from rest and increases in speed such that the acceleration tangential to that. So he has made it so that it is not a constant acceleration. And say where t is in seconds, if you determine the magnitude of the acceleration, it arrives at point B. Where's point B? Oh, okay. So I have to assume that that's right there. So you go 3 meters, you go this, and then you have to work your way out to the point. Oh, that's a headache right there. So he's taking his acceleration, turning this into velocity, and then somewhere he's going to have to figure out this distance here. So it's 3 plus that 2 pi r. Oh, and he does a quarter circle. So usually if you have a circle, it's 2 pi r, but he's only going this distance from here to here. And this from here to here. So that's why you have the 2 pi radius of 2, and you divide it by 4. You add the 3 meters because it was 3 meters coming up to there. That tells you how far you have to do this integral. And then you're wanting to pull or get your time out of it. Did he want anything else? Okay. Oh, you want to know the acceleration when you got there. You got to put in the acceleration here. That gives you the component. So you got 2 accelerations: acceleration tangential and acceleration normal. And so you get both of those. Square root of the squares. So there are weird things you could ask like this. So let's just take one. Actually, you know what I could do? I could go to the ones that I've assigned. Yeah. They'll let me in the I don't know. We'll cross our fingers and see if I've got to do a duo. Okay, I'm in the spring. I'm in this cliff. I do not remember, honestly, which week it was. Oh, word of the day. How about, okay, here. Oh, okay. Hat. I don't know. I just saw my hat on the table. So there. Now I'll go down. Open. Okay, you know what I'm going to do real quick? I'm going to go ahead and open week 6 and 7. Make available. Six. That was 6, I think. Okay, I wish I could go. You know what? I might be able to do that from the calendar. I was about to say, I wish I could go and pick off the weeks one at a time. But I might be able to do that from the calendar. So if I go to the calendar. Okay. So let's see. Is this one, is the bottom one that means? That is static. Well, that's the top one. There we go. So, okay. Yeah, I know it can't be the first. I'm pretty sure it's not the second. I'm almost sure it's not the third. How do I do this? Let's see. Control select. Okay. Open a new tab. Let's see. What? Okay, shoot. Looks like I'm going to have to go in there and do this. And edit this assignment? I'm not trying to edit it. Alright, well, I thought I would be able to get a shortcut by going to the calendar, but apparently not. I don't think you can't launch him as a connection, so alright. I'll do this. I don't think this one's it. Yeah, that's that is the erratic motion, which I did that, and shoot. This is one of the reasons I don't like Blackboard. You have to fumble around all the time. If that's the case, there's part of me that thinks that maybe it's in week 4. Nope. Maybe week 5. Okay, week 5. Gotta be here. Is it? Ah. So there's 2 videos. Okay, so this is the normal tangential. You'll probably see better videos there than you will of me doing this. Oh, okay. Well, shoot. I don't guess I gave any problems like that. Did I not give any problems like that? I don't particularly like that section anyway. But I did lecture on it here. But I tell you what I'll do, since I didn't give any problems there, I will go on to the next section and show you how they're similar. There's one thing that I'll bring up here, and that is when he did his little derivation, he did something interesting here. And that is this. And pay close attention to this, because what he's doing is he's taking a theta dot. So if you had, theta was in radians, this theta dot will be in radians per second. Now, with that in mind, let's head off into the next section. I just wanted to, because there's a similarity here. Okay, so now he's talking about curvilinear motion in cylindrical or polar, depending on the way you look at it, components. And what you have there is you're tracking things with an R, and you have a UR this direction and a U theta this direction. And so what happens is the write-up is pretty simple. You just have that. So the position vector is position, and it sounds weird. It points from the origin directly to the marble, and the UR goes along that direction, and then U theta goes along this direction associated with this theta. Then when you take the derivative, here's the big problem. The big problem is you're really supposed to do this rule where you have V R R UR, that's a vector, over dt. That's what this is. And so if you break it apart, what you have is the derivative placed upon the r, and then the derivative placed upon the ur. Now actually that occurs in Cartesian, but the thing is the I and j never move. The ur and u theta may actually, a second or so later, may have tilted over, so that now they're this way, as the particle moves in a circle. So then what he does is he goes through this really weird kind of way of deriving this, that the vector looks like this. Now this looks similar to the one previously, but the derivation could be done in a simpler way and in a way that makes a little bit better sense. And the reason I'm doing this is because it's beneficial when you're moving things around between coordinate systems. So let's say you had an I and a J, and you had a marble sitting here, and you had UR and U theta. Now, these move, change direction. The I and the J do not move. They don't change direction. And so the question is, okay, let's go back and see exactly which one he's doing first. He's doing the derivative of the UR. So if you're interested in saying, hey, what is the derivative of UR with respect to time? You just isolate yourself to this, so much so that I'm going to isolate and even remove that and say I am only interested in how that vector changes with respect to time. Now, what's funny is the only thing that does change with respect to time is theta. Now, R, or the distance, might change. It might, for example, the particle might sweep along here, and you're pointing to the marble and it's here, and a few seconds later it's here. But if you look back at this equation, the change in R is taken care of here. So we're only interested in the change of the direction of that base vector. So if you look at it, we're isolating ourselves down to where we're focused only on that. Now the next thing I'll do is I'll redraw J. And then I'm going to take this base vector and I'm going to stick it right here. Now I'm trying to do this. So each one of these, the UR, the J, and the theta are all the same length. And I haven't done a good job of making them that way. But I guess if I want to be like super efficient, let's try to make that so we can do the best we can here. I'm at 0 degrees. I'm going to go ahead here, there. So let's see, 1, 2, 3, 4, 5. I'm going to go, hang on. Come on. There. So we'll go ahead here. Come on. My eyes are goofing up here. The lighting is weird. 1, 2, 4, 5. It kind of, now on the screen, if you're in class on the screen, the aspect ratio of the projector might be such that they don't look the same. Do they look the same? Does it really? I think I did it. Say 1, 2, 3, 4, 5. Let me make sure. Maybe I did it wrong. Let's see. 1, 2, 3, 4, 5. Well, actually, the little arrowhead made it a little longer. But now I'm going to kick this thing up just at a random number of degrees here. Try to put it right here. Okay. 1, 2, 3, 4, 5. Okay, it doesn't look quite right, but it's supposed to be, they're supposed to be the same length. Now that I got that, what I'm going to do is say, okay, I can have a component of UR here, and a component of UR here. And remember, this is theta. So if I want to represent UR this way, it would be cosine of theta I plus sine of theta j. Now, you have to remember the length of this is 1. So usually you're supposed to have the UR, the length of UR, and the length of UR, because that's the length of this thing. But the length is 1, so I don't need any of that. Okay. So now I'm looking at this. Now I'm saying, hey, wait a minute. The only thing that changes here with respect to time is theta. So now I can go in here and do something really interesting. I can take the derivative of a vector u sub r with respect to time. Again, this and this one, no change with respect to time. Respect to time. Okay. So, ordinarily I would do this. Derivative of cosine of theta time plus I. Okay. Derivative of cosine of theta, derivative of I with respect to time. And then plus derivative of sine with respect to time times j plus sine theta times derivative of j with respect to time. But this and this are 0, and so I'm just going to do this. I'm going to do this. And then I'm going to do this if this pen will work right. And I'll just slide it right there. Now, that's easy enough. So u r dot, the big dot above it, derivative of cosine is minus the sine. And derivative of sine is cosine. Now we got an answer. And we say, yay, we got an answer. But what is that answer? Let's compare it by looking at our original drawing. This time we'll put our u theta back on there. And over here, I'm going to redraw this. Okay, give me a second here. You know what? Here's what I'll do. I'll do a copy and a paste. And I'll take this sucker, put it right here. Now, what I'll do is I'll draw back out my ruler. It was 38 degrees. Okay, what is 38 plus 90? 128? Is that right? Oh, no. So, okay, what's 180 minus? Okay, so 38. What is 180 minus 38? What's that? 142? Oh, shoot. Okay, wait a minute. I'm trying to find out. Okay, so here's the way he's measuring his angles. So there's 0. Look, it's 1 degree. It's 1 degree. So I got to kick it up so that it's 90 plus that. So, oh, geez. So in other words, if this is 38, that means this is 38. That means this is, what's 90 minus 38? What was that again? 52. Okay. So that's supposed to be 52. So I'm trying to be real precise here. And again, it's 5. 1, 2, 3, 4, 5. Well, okay, so you'll forgive me if I'm not touching the origin here. I tried to make it as best I could. So this is u theta. They are 90 degrees apart. Oh no. I guess I'm going to leave that there. Or I'll see if I can. I'm going to leave that 90 degree there. Hey, wait a minute. Now, okay, there you go. So they are 90 degrees apart. And if I'm interested in doing this, I can do this. Move the J out of the way. And look at the component back here. And actually what I'll do, I'll change its color. And I've got a vector back this way. So if I want to list u theta, it looks like to me, okay, this is theta and that's theta. So it looks like to me that if I'm looking for the I component, I'm looking at minus sine of theta I plus cosine of theta j. And now if you stare at this real close, there's something interesting between this and this. And that is, they're the same. So u sub r with a dot on top. Now, I have made one particular interesting error here, and that is this. I need to work on this to fix something. Okay? And here's what I need to work on. I have not done one thing. What did I do wrong there? So that you guys that are in calculus, y'all should see the error of my ways, right? What have I forgot? So let's say this was 3t. Sine of 3t. Take a derivative with respect to t. What is that equal to? Derivative cosine, sine is cosine, right? And then I need to take the derivative of what's in there, right? So I forgot that. So in fact, I really have to, let's see, find my color. Okay, so if I'm taking the derivative of this part with respect to time, that is correct right there. But what I haven't done, I haven't included the extra term, which is theta dot and theta dot. Now is that, am I making sense there? Because if I put in, put in something at random. Okay, let's say somebody said the sine of theta is, like I said, 3t. So theta was equal to 3t. So theta is just changing with respect to time as the thing is rotating around and around. So if I'm taking the derivative with respect to that, I have to include that derivative of that term in there too, like I did a second ago. So since I don't have the explicit function 3t, where this is still a function of t, then I have to carry that like that. Oh, did it? Oh, okay. Here. Wait a minute. Let's see. Math. All right. So it turns out that u sub r is equal to theta dot times u theta. Now, what was funny in that previous section, he said u sub r is equal to theta dot times u nor. Wait, his was n and this was t. So turns out that it's a similar component here. So if you go back to the book, he ends up with that same thing. And it's not too surprising. Okay, so hang on. If you look at this, okay, this is kind of weird. Okay, so let's take a look at why did UR end up here? And why did this end up here? Because if you look back at the equations, this was the case. Now, R dot just ends up here. And then this ends up here. Well, we realize that that's nothing more than theta dot times u theta. So this means r theta dot u theta. And so what you get down here is this extra term like this. So actually, I would prefer if he wrote another big box that had them written out. V is equal to r dot ur plus r theta dot u theta. But that's kind of what he's got, but it's better if you combine them. Anyway, the arrow here to move. Okay, and it's not too surprising that, and he goes through the similar argument, it's not too surprising that if you take the derivative of the theta, it becomes minus theta dot times ur. So, in fact, and the reason you want to do that, okay, what a pain in the rear here. So now, you want to find the acceleration. It's nothing more than this. But the velocity on the page before was r ur plus r theta dot u theta. Now, the first thing you do is take the derivative of one term, Then you take this term, oops. So that's what happens when you touch that's how this thing's supposed to work. You take the derivative, you leave this, I'm sorry, this is supposed to be a dot. So you have a double dot here. So you take a derivative of the first term here times the second, then derivative of this term times the first. So you see this. Well, you know this is going to end up being a theta dot u theta. Now you're working on this one. You got three terms. So you take the derivative of the r, derivative of theta, and then derivative of the base vector. But this one becomes minus theta dot ur. So they flip back and forth. And then you gather terms. Okay, and he shows that here. You gather terms, and you get this mess. Okay, so this is just unbelievable until you stare at this for a minute and you realize something interesting. Okay, so in the previous thing we had acceleration is equal to, I think he called it v, u tangent plus v squared over rho, but in this case I'm going to call it r, times u normal. Let's stare at this for a minute and see, hey, wait a minute, if something goes around in circles, they both have to come up with the same answer, right? So let's take a look at this. Let's say a guy's out here and he's driving around in circles. We're just going to take the simplest case where r is equal to a constant, which basically just tells you that the acceleration, the centrifugal, is just going to be, that's supposed to be n, by the way, v squared over r. Now, if r isn't changing in this context, that's gone, and this one's gone. So the theta, so what you have in your acceleration in the polar coordinates or cylindrical, to me cylindrical means you've addressed the z. Currently he's in polar coordinates actually. I have, I'll first do this one. Sorry, I should do the other one first. But minus r theta dot squared u r. Now, how is this and this the same? And at first glance, you would think, I don't see how they're the same until you realize that v was equal to, if you wrote v in the polar coordinates, r dot, ur plus r theta dot u theta. Now, let's stare at this and then stare at this and say, can't I do this r squared theta dot squared over r? Okay, now this upper term, according to this, is nothing more than v squared. And if you compare these in a numerical value, you'll realize I put the r on bottom, and this term totally is that term. But it's also that term. They're both the same. They're exactly the same. There's no difference between them. It's just written differently. If you go in and you take v squared over r, and then you say, well, v is r theta dot, and I square it. So I took it from here, and then you realize, oh, I just got an r theta dot squared. That is, in fact, that. So there's no difference between these things. It's different in the way you might represent them. And so, oh, now he's talking about cylindrical coordinates. Okay, cylindrical coordinates, really cylindrical coordinates have a z component. Polar coordinates don't necessarily have a z. So what's my battery at? Oh, I'm over my time. And my battery's, what is my battery? So I guess we'll call it quits. Where is my battery? Oh, it's getting low. I guess I'm going to have to bring my own extension cord in here. At least it's a two-prong cord, so